Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas?
Why do some things glow in the dark?
Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. What's happening in the world of science for you?
Oh, well, lots of things. Of course, it's sort of post-Large Hadron Collider.
Oh, that's the thing.
Welcome to Financial Meltdown Week, isn't it? Everyone thought there was going to be a black hole because of the LHC, and instead there's a black hole in the world's finances. Maybe the black hole has surfaced somewhere else that we hadn't anticipated. But, no, I think the whole business on the sort of economic front has sort of turned people's attention quite abruptly away from science and onto the financial front and what their financial fortunes will be in future. But that hasn't stopped scientists still publishing some pretty good and exciting things. I was just looking at what's been happening this week, and there's an interesting bit of research that's come out of some researchers at Penn State University in America. This is a guy called William Brower. What he and his colleagues have done is to write a piece of computer software which can go to web pages, and if someone's published some data in the form of a graph, the good thing about graphs is that they make lots of data very easily interpretable, so you can see a nice picture and immediately turns lots of numbers into something visual that we're very good at interpreting very quickly. The downside is that when you want to then take the data that made the graph and do other things with the figures, if all you've got to look at is the graph, then it's really hard. So what this group have done is to write a computer program that can go through a web page, find the graph on the web page, interrogate the graph, even though it's only a picture, and work out what the original numbers must have been to draw that graph. And then they produce a table of the data for you, and the idea being that then you could compare their data with, say, your data if you're working on similar things. Or if you're a sports fan and there's a certain team or a player's form listed there on the internet, and it's in graphical format, then you could grab that graph and you'd have lots of data on your spreadsheets on your computer, so you might know which person to bet on or how your favourite team was performing. So it's a really good idea. Don't know if it's actually going to work very, very well yet. I mean, they've only just produced this provisional version of the programme, and they've also published this in the archive.org on the internet. But at the same time, very exciting, so it'd be interesting to see what they can do with this.
Absolutely. Gosh, it's never ending, is it, all this science stuff? We've got some questions coming thick and fast for you already, Chris. So Angela in Trimley says, I have a question for the Naked Scientist. Why is it that when I shut my eyes after looking at bright things, I can still see it, but in negative for a while?
That's actually a fantastic question. Thank you, Angela, for that, because this is basically fundamental to how your eyes work. Because in order to make a sharp image on your retina, that's the part of the eye that converts light waves into nerve signals the brain can understand, you have what's called lateral or surround inhibition. Now, the best way to think about this is if you have a sharp edge, the only way you can get a sharp edge so you can see where something ends is by making sure that cells there are at the boundary are turned off abruptly. And the way the eye does this is by having a population of neurons called horizontal cells in the retina, and these are inhibitory. And what happens is that when a spot of light lands on one bit of the retina, it turns on the photoreceptors, the nerve cells that are light sensitive in that area, but it also turns on these horizontal cells which go away from the illuminated area, and they try to switch off all of the cells around the illuminated area. And what this does is to inhibit the cells around the illuminated area so they are strongly off, and those which are strongly on, therefore, are the ones that detect the light. So you get a very defined, a very sharp image formed on your retina by spots of light. Now, if you then take the light away, so in other words, you've looked at something bright against a dark background, for example, if you then shut your eyes, suddenly the inhibition that was being waged on the cells around the area is withdrawn, and the cells that were activated suddenly decrease their activity. And so what you get is a little bit of rebound activity in the cells that were inhibited, switched off, and you get a reduction in activity in the cells that were turned on. So you see a sort of negative effect. You see the inverse effect of what you were looking at, just transiently, while the retina resets itself.
Wow, that's really quite something, Chris. Our eyesight is always... Mine's failing just a little bit. I do have to have my specs, of course. Now, our next question, Chris. Agnes in Braintree says, Hi, Sue and Chris. When I was younger, when I went to the doctor, they used to examine my tongue. My question is, what can be determined through this?
Oh, there's quite a lot of things, actually. One of the things you're looking for is, have they got a sort of smelly breath? Because if people aren't eating properly, they have sort of smelly breath. If they have diabetes and they are becoming what's called ketotic, they're breaking down fat, then they smell of acetone, and that can be a giveaway. Also, if people aren't eating a good diet, or if they haven't eaten properly, or they're very dehydrated, then their tongue can show furriness and those kind of signs. You can also get infection in the tongue. You can get what's called a strawberry tongue. That's another example. You can also get swelling of the tongue, and you get redness of the tongue if you're deficient in iron. So there's lots of examples of things that can be manifest in the mouth, and there are clues that you can get from looking in the mouth. And if you look under the tongue, you can look for what's called central cyanosis. This is a bluing of the veins because there's not enough oxygen in the blood. So there are lots of clues that you can get by looking, and that's just part of the body that you look at when you do a sort of general overview of someone.
Now we know. Thank you very much, Chris. Colin says that we're always being told to turn off our standby buttons and such. My question is, does this equate to clocks on cookers, etc.? Because surely if you turn these off, the time will be wrong when you turn it back on.
It's a good point, isn't it? It all depends on whether the electronics running the clock is wasteful or not. The reason people tell you to turn your televisions off by unplugging them is that in some cases, and certainly my computer is like this, the electricity goes into the power supply because lots of the electronics inside the television, inside computers and other pieces of equipment don't run at mains voltage. They're transformed down to usually DC and usually 5, 12 or 20 volts. Occasionally other voltages between them somewhere, but usually that's about it. So you need to run the transformer all the time in order to supply that voltage. Clocks, for example, definitely are running at something like 5 volts. And as a result, if you're running a transformer, you're wasting energy because the transformer will emit a hum, so it's making some sound energy. It will get warm, so it's producing some heat energy, and that means that you're not turning all that electricity into lower voltage electricity, so it's wasteful. Then you've actually got the electronics themselves. You're making light energy from the clock and any other things or other bits and pieces and peripherals that are on the piece of equipment. And you're also obviously producing some heat because the electronics will themselves produce a little bit of heat. So if you unplug the item and it doesn't have a clock that you need to keep the time, then you will save some electricity. And I think the argument here is, OK, one television or one cooker, one microwave isn't very much. But if you sum the entire total in your house, it does equate to a reasonable amount of electricity saved. And if you sum a whole village, and then a whole series of villages, and then whole towns, and then cities, actually on the global scheme of things, this is a huge amount of energy that's being wasted just in the name of keeping a little red light on your television so that you can press a button to turn it on rather than plug the plug in. So I do actually try and unplug things, although it is difficult when plug points are not very accessible, and especially if people are older and they don't want to keep bending down or trying to reach behind things to put plugs in. It's very tempting not to do that. So I think we need to perhaps consider making electricity supplies easier to access, and that will probably encourage people to turn things off rather than have them on standby buttons.
In fact, Chris, why couldn't we have a remote control that would turn off the power source?
Well, that'd be a bit dodgy if you had some things that were absolutely dependent on power, like your lights, for example. This may get dangerous in the dark. Some people may have home oxygen machines because they have difficulty breathing, and it would be rather dodgy to turn those off. But I think a little bit of sensibility here, obviously. It's more about giving thought. Are there things which I'm leaving on which I probably could unplug? The answer in most people's cases, and certainly in my case, is definitely yes, I probably could make the effort and unplug certain things. And it all comes down to laziness. And if you can motivate yourself to unplug things, then you will save a little bit of electricity for yourself, but you will definitely save a lot of electricity at the level of the population if everyone does this.
Thank you very much indeed. Now we have Tony on the line. Good evening to Tony. How are you?
I'm very well, Sue. You sound lovely as ever.
Thank you very much. You're through to Dr. Chris. What's your question?
Right. Human beings are basically animals. I don't mean that in the nastiest way, but we have to be very careful when we're eating, as regards wash, hygiene, and yet dogs and most other animals don't seem to have these problems. Why is this?
As in terms of us getting food poisoning and things,
yes,
Tony?
Yes, exactly, and all that sort of thing.
Yeah, the answer is that we've evolved to be a bit soft. Animals that have to live their lives in the wild are very good at fighting off infection. And rats, for example, are almost impossible to infect. If you take a rat, and I'm not advocating you do this, but if you were to make a hole in its skull so you see its brain, for instance, the rat would not die of infection. But if you did that in a person, the human would almost certainly develop overwhelming sepsis and would die. The rats' immune systems are absolutely incredible, and I think they're being exposed to muck and dirt from the minute they're born, so they are very well educated, immunologically speaking. They have a very broad repertoire of antibodies and a very good ability to fight off infection, and the same goes for their guts. I think also animals which have evolved to eat dirty, mucky food, so in other words, they're carrion feeders, have a very good gut immune system as well, so they're very resistant to the kinds of infections that they might pick up. Us humans have got quite a few million years now of selection about being a bit fussy about what we eat. We've also been cooking food for thousands of years. Scientists think at least 50 or 60,000 years we've been cooking food, probably more. And as a result, we've basically lost the ability to be as hardy as we probably once were. And as a result, we're more vulnerable to gut infections. The other thing that is a worry is that our population is very, very high. And we also tend to congregate ourselves in cities. And when we live in such high densities, we make it very easy for infections that one person might have to transmit into another person. So salmonella, for example. And under those circumstances, we're obviously making ourselves more vulnerable to infection than if we were out as hunter-gatherers, where there wouldn't be so many humans who could harbour things like cholera or salmonella to give those things to us.
Do you think that when you're older, I mean, I'm getting on now, and do you think because in our youth we didn't have all this business that we're more tougher like the animals?
Well, it's possible, Tony. There's a number of factors here. One of them is the spectrum of bacteria that your gut picks up when you're little. And we know for a fact now that, and this was underappreciated for a very long time, that the microbes that live in your gut play a huge role in your health. Not only do they make you healthier and they help you to extract energy from food, and they also produce some vitamins for you, the bacteria that live in your gut also protect you from getting infected with other things. If you lead too cleaner a life, then it's possible that you may not have the broad repertoire of bacteria in your guts that someone who does lead a bit of a dirtier life has. Therefore, you might be more vulnerable for that reason. And as your immune system undergoes a lot of its education by exposure to dirt and bugs, it's possible that people that did have exposure to dirt and bugs when they were young and their immune system was very young and had the ability to respond very powerfully, they may have developed a very good repertoire of infection-fighting immune elements when they were little, and they've carried that into older age. I think there's probably a number of things going on, and it's not as simple as saying, I was born 50, 60 years ago, therefore I'm healthier than someone being born today. I think a lot's changed since then, but certainly we need to consider that our lifestyle can have a major impact on our health, possibly by affecting the bacteria that live inside us.
Oh, I was in Burma during the war. I expect that helped.
Tony, thank you very much indeed.
Thank you, Sue.
Thank
Bye-bye.
you. Bye-bye. Dr. Chris, we have a question here that's been emailed in from Gus. He says, what is the link between stress and obesity?
Well, I think it depends which way you want to look at this. I don't think that there's any evidence that stress causes obesity, but depression definitely can. And if people get stressed chronically, they can get depressed. And when people get depressed, they get anxious and they may comfort eat. They may also not sleep properly. And both of these things have been linked to changes in weight, quite dramatic changes in weight, for two reasons. One is that people who tend to get depressed might find comfort in eating high-calorie, high-sugar foods. And there's evidence, for instance, that chocolate produces a big surge in hormones when you eat it, and this can make you feel slightly better. And also, chocolate does contain a number of stimulant compounds. Apart from caffeine, which is sometimes added, it also contains things like theobromine, which are weak amphetamine-like agents, and these can help to pep up mood. So this means that people may be tempted to eat the sorts of foods like chocolate, which make them feel a bit better, but also make them put on weight. Because they put on weight, they then feel worse, because they think, I'm getting fat, I don't want to get fat, and this makes them more anxious, so they eat more chocolate, and this sort of builds up. There's also evidence that's emerged in recent years that people who don't get enough sleep are prone to putting on weight. And this is really interesting, and it's only in the last few years that scientists have begun to get a handle on this. There's a hormone called ghrelin, G-H-R-E-L-I-N, and it's produced by a certain population of cells in the wall of the stomach. And interestingly, ghrelin boosts appetite, so it's a hunger hormone. And it seems to also be tied to how long you spend asleep. And scientists found that people who were sleep deprived tended to produce more ghrelin than people who got enough sleep. And so if you have depression or stress or anxiety, people often complain of disturbed sleep. If they don't sleep enough, then they could be producing too much ghrelin, and this might make them too hungry or more hungry than they should be, so they take on more calories than they actually need. And scientists have done studies both in teenagers and also in adults, showing that an extra hour in bed can paradoxically make people lose weight. There was a study which got published from researchers in Boston in America, which looked at children, and they found that children who had less sleep were about 25% more likely to turn into obese teenagers and then obese adults than teenagers that got more sleep. And it seems paradoxical to think that sleeping more makes you thinner, but I think perhaps that's the link.
I just love chocolate, Chris, you know that. So anytime you've got any spare, I'll just eat your chocolate.
Yes, you frequently do.
Thank you. Now then, we have our studio guest, Jason Carter, who's here with his harp guitar, which you're going to love. But he has a science question for you, don't you, Jason?
I do indeed. Hi, Chris.
Hi, Jason.
I've been living in Finland for 6 years, and the first winter I was there, it snowed from October till April, and it was like a real winter. And then suddenly, it's been... Well, the next winter was maybe a month and a half, and then since then there's been only 2 to 2.5 weeks of snow every winter, and of course all the Finns are blaming it on global warming. But can it change like that dramatically in one winter? And it hasn't been. It's getting like warmer and warmer, of course. But from a very serious winter when it was minus 37 in December, and of course 1.5 meters of snow, to now nothing at all in 1 year, almost 1 year. And if that's the rate of change in the weather, if that's like how it's going to be for the next 20 years, it's going to be like the desert in about 20 years' time.
Well, there is evidence that the Earth's climate can change very, very dramatically. We tend to think of planet Earth's systems as a bit like an oil tanker, meaning that when it's going in one direction, if you want to change direction or even stop it, you've got to throw it into reverse miles ahead of the time that you want it to do anything.
Okay.
There's always a sort of overshoot. But at the same time, that doesn't mean that while things are taking a long time to change elsewhere, there won't be other systems or other territories at the margins which are seeing quite dramatic effects.
Right.
For instance, there used to be civilizations flourishing where there is now the Sahara Desert. There used to be, for instance, about 30,000 years ago, 40,000 years ago, Australia, we think, wasn't desert at all. We think Australia was covered in lush rainforest, and we've got the fossil record to prove it. And then all of a sudden, it dried out and became completely desolate, and the Nullarbor Plain in the south of Australia sprung into existence. The likelihood is that you probably can see quite dramatic changes quite quickly, because it doesn't take that much of a difference in temperature to determine whether something snows or whether it rains. We're talking about actually quite a narrow temperature range. So I think probably you'd be a bit... I mean, how would you expect the weather to change? You wouldn't expect it to sort of snow a bit and then not snow at all. You'd expect what would probably happen is it just would change.
Okay.
And it might be that you would get a run of bad days, a run of bad years rather, when you have a lot of snow, a run of less bad years. And what will happen is probably the relative ratios of those will change gently over time. And then you'll end up with a new weather or a new local climate establishing itself. The real answer to the question is no one really knows, because we've never been able to measure what goes on for long enough across a big enough series of different systems to get good enough data to understand exactly how the weather changes, how climate changes, or even how we're able to manipulate the system by our own activities.
One last question. Could it be sunspots? Could that be causing this like brief sort of warm thing in Finland, especially when it's been from a drastic winter, sort of 7 months of snow to nothing?
Well, sunspots definitely can affect the weather. There was a time in the 17th century that was called the Maunder minimum, after Maunder, the person who discovered this. And he had noted that there was a period of very, very low sunspot activity. And what they correlated this with was a period of very cold weather. The temperature dropped by several degrees across Europe and Italy. And this translated into a mini sort of ice age come mini cold spell for quite a lot of Europeans. So yes, the sun's activity can definitely make a difference to the Earth, and it can definitely make periodic changes, but we think the sunspot cycle is about 11 years long.
Okay.
So we shouldn't expect to see the repercussions lasting too long. The sun's been there for a long time, the Earth's been here for a long time. We wouldn't expect it to suddenly change tomorrow. So yes, sunspots definitely make a difference. Whether they'll be able to describe what we're seeing now, I think the answer is no. People have looked very, very hard for an external explanation for the change in temperature signal and the warming signals that we're seeing on Earth, and they haven't been able to find one. So that leaves the blame, unfortunately, currently resting at our doorstep.
Yeah, great. Thanks, man. Thanks a lot.
Right, that's Jason's question. Now then, Dr. Chris, Paul in Norwich says, can he put an alternator on an electric car and never have to charge the battery? From Paul in Norwich. What do you reckon?
Oh, if only. The answer to this is no. Unfortunately, that would be a perpetual motion machine, and there's no such thing in the real world as a free lunch. Basically, what Paul is suggesting is that you have an electric car, you have an alternator connected to the car. As the car goes along, it also turns the alternator produces some energy, and this charges up the battery, and the whole thing goes around in a circle. But what that doesn't explain in the equation is where is the energy to move the car in the first place and keep the car going, because all the time the car is moving, it's fighting against the air, it's causing air resistance, it's effectively producing heat in the air molecules. That energy has to be provided from somewhere. So the whole system would continuously be losing energy, and so you would never actually get anything back. So no, unfortunately that won't work. If only it did, all our energy problems will be solved.
Indeed, wouldn't they just? Paul Anderson in Buckingham says, hi Sue, I'd just like to throw my comments on this microwaves on standby issue into the ring. Over the lifespan of your microwave, it's very likely you will spend more money on electricity to power the clock light than you will on the actual function of cooking. Maybe he doesn't eat a lot. And Dave in Bradwell says, I was just listening to Tony's question and it reminded me when you used to go to the shop and buy cheese in slices from a slab on the floor and you'd get sugar and flour out of a sack, once again kept on the floor. Very true indeed. It's Ask the Naked Scientist, and a couple of questions coming in. Dr. Chris in his armchair laboratory. Anne says, hi Sue and Chris, my question is in regards to this disease affecting the honeybee at the moment. Is there any development on it? For example, the cause and possible solutions?
This is a tricky one. What Anne's talking about is a phenomenon which is called colony collapse disorder, or CCD. And originally, when this began to happen in the US, where it's really been a big problem, people have lost their entire bee stocks, for example, people blamed it on something called the Varroa mite. This is a tiny parasite that is carried by bees, and it lives on the bee, and it basically does to a bee what a flea would do or a louse would do to us. It drinks small amounts of blood and multiplies, and when bees go into their hives, they spread these things amongst the colonies, and so people thought perhaps the Varroa mite, because they're drinking blood, perhaps they're transmitting infections from one bee to the next. But scientists recently did some studies where they took the mites and they did genetic analysis to look for signs of infection transmission between bees, and they couldn't find any signs of viruses that were capable of persisting and amplifying in these mites, and so they wrote that theory off. So people still are a bit of a loss to explain what this colony collapse disorder is, but it's potentially going to cost billions, because bees are the unrecognised workforce which keeps our countries productive, and it keeps our farmers in business, because bees literally contribute billions of pounds to certainly the British economy, but internationally it's billions of dollars too. And the reason for that is that they pollinate things, and it's pretty trivial to think, oh, well, you just have some pollen, but plants produce fruits only when they're pollinated. So the fruit that you see, and that doesn't matter whether you're a grass or a cereal or whatever, if you're an insect-pollinated plant, you can't produce fruits, and therefore you can't produce a yield if you're not pollinated. And bees do a huge amount of this. And if we lose our bees, we could be in real trouble. So that's why people are so worried about honeybees and the declining numbers. And we really need to find out what this problem is and solve it before we face not just a loss of bees, but a loss of revenue and an economic downturn because of produce. Because if we don't have bees, we don't eat.
And we don't get our honey either. Now, Bill is on his tractor. Hello, Bill. Thank you very much for calling into the programme. How is the nuclear fusion programme progressing, asked Bill. What do you say, Chris?
Well, in recent years, there has been quite a lot of steps forward, because there has been international approval for a project called ITER, which is the International Thermonuclear Experimental Reactor, ITER. It's going to be built in France, and work has actually started. And this is going to be the first example of something that might produce some energy. At the moment, fusion reactors that have been built, and let's just summarise, what is nuclear fusion? Well, nuclear fusion is where you take small atoms and you join them together to make bigger elements. So you might take, say, hydrogen and join hydrogen to another hydrogen, and you get an atom of helium instead. That's nuclear fusion. And when you merge the two different hydrogen atoms together to make a helium, you release some energy, and the energy could be tapped off to A, sustain the reaction, and B, then produce electricity, because you could heat water, for example, and turn that into steam and drive a turbine. So that's how it works. We know it works because the sun is powered by nuclear fusion, and the sun is the biggest nuclear reactor we know about. And that's the problem. The sun is absolutely huge. You could fit 1 million planet Earths inside the sun with plenty of space to spare. That means the sun is incredibly big. It means that the sun has a huge gravitational force pressing its contents together, squeezing things very, very tightly. And the centre of the sun's at about 15 million degrees, so it's very hot. And all those factors combine together to make it quite easy for the sun to have nuclear fusion. What scientists are trying to do is to recreate that on Earth. And that means we have to produce something, because we haven't got the gravity to help us, we need to produce something which is capable of generating temperatures of about 100 million degrees and confining whatever the reaction is in a space. And so you've got several problems. You've got to keep it that hot, you've got to keep it in one place, you've got to feed in fuel, and you've got to tap off the energy it produces. The ITER is the best chance we've got yet of working out whether we're close to achieving that, and that's what scientists are working on. But at the moment, no one has managed to make a fusion reactor that does anything really more than just produce the same amount of energy that it consumes. Certainly, we're nowhere near being able to reproduce nuclear fusion at a level that would be environmentally useful or energetically useful. And the benefit of fusion is that the waste products aren't like the products of fission, where nuclear fission produces lots of highly radioactive materials that are around for a very long time. The products of nuclear fusion are largely short-lived things, and they also tend to produce more of their own fuel when they run. So they're much cleaner, and that's why people are interested in them. But we're nowhere near yet, I'm afraid, Bill.
Thank you very much, Dr. Chris. Colin has sent a text in. He says, how many wind turbines in a row would it take to reduce a high wind by absorbing all the energy?
I think far too many to count. Because if you think what the wind is a huge amount of air moving because it's been heated up in one place and it's moved away, and then there's cold air coming in to replace the hot air that's risen. And so you've got these big gusts of wind, lots and lots of gas moving all at once. The amount of energy that's in that is absolutely tremendous. If you think how much energy the sun is putting into the Earth all the time, every square metre of the planet's surface is being hit by 1 kilowatt. And if you add that lot up, it's gigawatts of energy, probably petawatts of power, which is landing on the Earth's surface. And this is heating up the air. So in order to slow down and stop that much wind would be a huge amount of windmills. I don't think we've got enough land area to have enough windmills to actually make a difference to the wind, to be honest.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.